Let's take a look at an interesting example of applying true velocity vectors. In this particular case, we have a guy who wants to cross a river in his boat. So he's starting here, let's say, and he crosses the river and he wants to hit land due north of his starting position, so something like this. The boat's traveling at 20 miles per hour and the river is flowing due east at 7 miles per hour. In what direction should the man head his boat? Well, just using common sense, we can see that in order to end up directly north with the current flowing due east, he's going to have to go in a northwesterly direction. The question is exactly what direction should he head his boat? So we have to know like precise angles, and we can do that using vectors, specifically true velocity vectors. So the idea is this. We would take the boat vector plus the river vector, and those two added will give us the true velocity vector. Okay, so we try to fill in as much of this as we can. The boat vector we already saw is going somewhat northwest, and we know that its magnitude is 20. The river vector is due east at 7 miles per hour. And the true velocity, this is the real key here. The true velocity is the vector that represents the path of the boat, the speed and the direction of the boat when you take into account what the boat's trying to do and what the river's trying to do. So in that case, that would be the due north vector, right? The idea is when you factor in all the components, the boat will go due north, and so that represents your true velocity vector. Now we don't know the magnitude of that vector. We don't know how fast that true speed will be, so this is all we know. So now if we set this up with vector arithmetic, we can start to fill in some pieces, right? So this vector would be written component-wise like this, and we don't know either one of the components, right? We don't know the horizontal or the vertical yet, so we'll see if we can figure those out. The river vector, however, we do know is exactly 7 horizontal and 0 vertical. Now the true velocity we don't know, however, we do know that it has a 0 horizontal, right, because it's completely vertical vector. Now we sort of work backwards to fill in the blanks. If I add this horizontal component with this horizontal component, I get this horizontal component. That tells me that the horizontal component of the boat has to be -7. So this right here has a length of 7 in this vector. Then, once I know that this side of the right triangle, I can easily find the other side using the Pythagorean theorem to be the square root of 400 minus 49, which is 351. Okay, so this vertical component is square root of 351. Now we don't have to find all of this information to answer the question, but we might as well fill in our vector arithmetic as best we can and then answer the question because it's simple to do. Okay, now this vertical component plus this vertical component should equal this vertical component. So that means this vertical component on the true velocity will be the square root of 351 also. Now let's answer the question. In what direction should the man head his boat? So that's dealing with the boat vector. What direction is that vector? Well, let's find out. If we draw it again over here, it looks like this. This is 20. This is 7. This is the square root of 351. And we want to know the direction. This is our arrow here, so we're definitely going in a north something west direction using our knowledge of bearings. So the question is, what angle goes here? So if this is my starting point, I get my north reference, and then I need to know the angle from north to get that direction. So this is the guy I want. Well, in order to do that, let's figure out theta inside my right triangle. Theta, using just regular right triangle trigonometry, I'll use the adjacent and the hypotenuse. So theta would be the inverse cosine of the adjacent over the hypotenuse. And that's approximately 69.5 degrees, which means that this angle here would be 90 minus that, or in other words, 20.5 degrees. So this is our answer. That's the direction he should head his boat to counteract the river to end up due north of his current position. Now again, the emphasis of true velocity is you simply add all the vectors together and they result in the true velocity. You're not always trying to calculate the true velocity. Sometimes, as in this case, it's given and you fill in the other pieces of the problem.